f of xy here is a function of two variables x and y. To evaluate x and y, we specify the values of the two variables. X is 2, y is 1. We plug in 2 for x, we plug in 1 for y, we evaluate the function. So we get the value of the function f at the point 2, 1. Now, we've got a value of a function at a point in the plane. How are we going to represent that graphically? Well, the plane will be our xy plane, and the value of the function will go in the z direction. So that if x is 2 and y is 1, we have the point 2, 1 in the xy plane, and that's the point 2, 1, 0 in the xyz coordinate system. And from that point, we go 25 units in the z direction, and we get the three-dimensional point. And I haven't actually labeled that, but that's the point 2, 1, 25. Is on the graph of z equals f of x, y. Okay? Now, I mentioned that if we have a little rectangle out here someplace, we could take the coordinates of, let's say, this point and plug them in, and we get some z value. Now, if the scale is what we say it is, the z value is going to be a lot bigger than this, but just looking at a general function, we'll have some z value, okay? And then we're going to get the point corresponding to this set of xy values. Now, if we know the dimensions of this base and know this point, then we know what this point is, this point, and this point. So we can evaluate the function at these 3 points, and we can complete this figure. So we have something that looks like this, and this ought to look familiar to you, because you've got something very similar that I cut out of a piece of wood, and you did measurements on it. You found the vectors parallel to the sides, you found the cross products of those vectors, you found the normal vector to the plane of the top, you found the equation of the plane normal to the top, assuming that that normal vector applies at this point, which isn't quite true for a function like this, because these sides really don't coincide with the actual curvature of the graph of this function. Okay, this function has a graph. Right there's a preview. That's what it looks like. Just an elliptic paraboloid, and not difficult to see that. We'll see that in a minute. So these sides here are just linear approximations of this actual behavior of the function. The function itself will curve up away from these sides a little bit, or down away. In this case, it would be pretty much up and away. Okay, so we want to understand this in terms of the exercises you did with the block of wood, because that picture is going to be very relevant throughout Chapter 4 and well beyond. Okay? Well, now, another way to a way to actually picture the graph of this function, of course I've got one drawn over there, but we'll see how this builds, is through level curves. A level curve is a curve that you get when you set f of xy equal to some constant number c. So, what does f of xy equals c mean? It means 4x squared plus 9y squared equals c. F of xy is 4x squared plus 9y squared. F of xy equals c means 4x squared plus 9y squared equals c. Okay? Now we can investigate this, what happens to these level surfaces as we change the value of c. Before we do that, let's identify our function, our graph. What kind of a what does our graph look like, or what kind of a thing is our graph? Well, the graph is the set of points where z equals f of xy. Well, z equals f of xy becomes z equals 4x squared plus 9y squared. What kind of a graph do we get from that? Well, if we put it into standard format, we see very clearly it's a graph of a quadric surface, and if you're pretty good with quadric surfaces, as many of you seem to be, we can see that this is going to be an elliptic paraboloid, and it's going to look something like that. But let's first pretend we don't know that, because we don't always know what this thing's going to look like. It won't always be a quadric surface. However, we can still attempt to find our level curves and get some idea of what slices of this graph look like as we change our value of z. Because of course if we set f of xy equal to some constant, that constant is going to be our z coordinate, since f of xy equals z, and z equals constant gives us a plane parallel to the xy plane at some distance above or below, depending on the value of z, which is of course the value of c in this case. Okay, so to find the level curves for, let's say, just c equals 0, 1, 2, 3. Okay, well, if c equals 0, then our level curve is 4x squared plus 9y squared equals 0. And the only solution to that is for x and y to both equal 0. If either x or y is non-zero, then we're going to get a positive number for one of these, and the other number, neither of these numbers can be negative, so the only possible solution is x equals y equals c. So that in the z equals 0 plane, which is the xy plane, the only point on this graph is at the origin. Okay? Now, if c equals 1, we get 4x squared plus 9y squared equals 1. Well, you recognize that as the equation of an ellipse, and it's not quite in standard form, because the standard form has to have x squared divided by something, y squared divided by something. Well, I leave it to you to put it in standard form, but the standard form is going to be x over 1/2 squared plus y over 1/3 squared, giving you your basic rectangle, 1/2 here, 1/3 here, up at the z equals 1 level. So let's go ahead and do a graph here. Now there's an extraneous plane here. Just ignore the purple stuff. We go up to z equals 1, that would be here, and it's kind of been obscured, but I constructed this rectangle. It's a 1 by 2/3 rectangle. Half of this dimension is 1/2, so it's going to be 1, and half of this dimension is 1/3, so it's going to be 2/3. And then I just sketched the ellipse within that rectangle, making sure that the vertices of the ellipse occurred when the ellipse was tangent to each of the sides. Okay, so we had that. So at that point my picture pretty much looked like this. Okay, here we have this, this, this. Here's the z equals 1 point. I go 2/3 of a unit this way, 1 unit this way, going equal distances from the axes, and I get this. And now I sketch. The ellipse. And of course I have the point at the origin. Now at this point I didn't sketch, the parabolic picture, but we'll get that very shortly. Okay, well, I don't want to go to the plane z equal 2 or z equal 3, because we're going to have to divide by this number, and then we're going to take the square roots of the denominators, and we're going to have square roots of 2 and square roots of 3. And it's a little messy. Besides, you get a better picture if you just skip to c equals 4. And we see that we can easily see that rearranges to x squared over 1 squared plus y squared over the quantity 2/3 squared equals 1. Well, that gives us a similar picture to this, but it's up 4 units high, so we have to come up here 4 units. Maybe that's 4. And the dimensions here are going to be double the dimensions here. Here's a picture of our rectangle that would occur in the plane where c equals 4, which is the plane z equals 4. So we come up here and we sketch our somewhat bigger rectangle. I'm doing this kind of sloppily, but you get the idea. It's not going to come out quite as pretty as this one, but it'll be okay. All right, we get that. And we understand now that the higher we go, the bigger the number we're going to divide by over here. And that's going to give us bigger and bigger numbers for our A and B. Also, we didn't actually talk about it, but our slice parallel to the YZ plane is going to have x equals 0. We're going to have 9y squared equals z. Z equals 9y squared, which is going to give us a parabola in the YZ direction. And if we do the slice through the XY plane, at the XZ plane, y is going to be 0. We're going to have 4x squared equals z. We're going to have a parabola in this direction. So the whole thing is parabolic. So I'll draw kind of a parabola here, and a parabola here. And I could draw the parabola in the x direction. And then I can just kind of shade or sketch little arcs of the ellipses we would get at various levels. And I've got a picture that's kind of similar to this one. Okay, and there's a picture of this graph. Now we want to talk about some characteristics of the graph, but we now have some understanding of a function of two variables and how it might be graphed, and how in many cases it might well give us a quadric surface.